Slide 8. So we know that climate has changed over Earth's history, and we have some data to help us identify what the climate has done in certain parts of the world over geologic time. And we'll talk about some of that data in a bit. But for right now, I want us to look at this graph. It's actually 3 graphs out of your textbook, and they have very different time periods associated with them. So the top graph covers about 70 million years of Earth time or geologic time, with 0 or present time over on the far right. And then as we move to the left, it goes back in time over 70 million years. Now, there are little blue dots here on this graph, which have been collected from around the world, different kinds of data sets. It could be pollen records, it could be sedimentary records, it could be tree ring data. But whatever the data set is, it gives us a sense. It doesn't give us an actual temperature value, but it gives us a sense of, was the climate warmer or colder than it is today? So huge amount of geologic time, only a few data points in there, really. Okay, if you counted up each of those blue dots, how many are there? Not that many if you're covering 70 million years of Earth history. But we could say we could fit a best curve line to that, which is what's been done in this data set. So you see a red line in there. And it looks like from this data that actually Earth was warmer, say 55 million years ago, and it's been cooling ever since. So now let's look at the middle graph. So the middle graph covers a period from present 0 years there on the far right of the x-axis back 150,000 years ago. And now we're getting to see some more fluctuation in this data set. So we can see some periods when it's warm, then it goes down, it cools off, and then it warms again and cools. And so there's this sort of up and down kind of pattern going on. One of the things that's quite striking about this middle graph is that approximately 10,000, maybe 12,000 years ago, there was a very sharp increase in temperature, and it's stabilized since then, and it's kind of been hovering around that same temperature for, say, the last 10,000 years or so. All right, now let's look at the bottom graph. Now, the bottom graph, how they have analyzed this data is they've taken an average of what Earth's temperature has been like in the period between 1961 to 1990. So they've averaged, say, 30 years of temperature data, real hard numbers. And then comparing what has temperature done each year for the past 1,000 years. And we have pretty good data sets for the last 1,000 years, very robust. And what we can see is that in the last, say, 200 years, so since the late 1800s, so maybe not quite 200 years ago, but temperature has, we've had a sharp warming period, and it seems to just keep going up. So I'm hoping that you will look at these graphs and be a little bit skeptical, okay? Because we always have to be skeptical when we see data and try and understand, well, how is the data collected and what is it representing specifically? So a couple questions that I'm hoping that you're already thinking about is, first of all, were these temperature changes uniform worldwide? Where are we collecting the data from? Are we collecting the data from a region at 50 degrees latitude? Are we collecting it at 80 degrees latitude? Are we collecting it at the equator? So are these data sets representative of what's going on with temperature around the world? And the other question that I want you to be asking yourself is, how is this data gathered? Okay, who's collecting the data, and what techniques are they using, and how certain can we be of these data sets? Okay, slide 9. So one of the data sets, the most robust, strongest data set that we have for determining past climate is the ice core record from Antarctica, from the interior region of Antarctica, which even over that period of 800,000 years, geologic kinds of timescales, has been pretty stable in a continuous ice record. In other words, even when the Earth's temperature has been warmer, For the last 800,000 years in Antarctica, we have every year some kind of snow falling, and that snow captures atmosphere in it, in little ice bubbles. And by drilling through that ice sheet in the center of the continent, we can literally see year by year, and notice the picture here on the right, layer by layer of ice is an annual cycle in snowfall. So what kinds of information does that ice core record give us? Well, one thing it gives us is the concentration of carbon dioxide, how much CO2 there was in the atmosphere every year for the last 800,000 years. It also records or collects particulates that are in the atmosphere each year, because the winds blow, the high level winds carry any kind of volcanic eruption, wildfires, meteor impacts, etc. That aerosol or particulate matter will get embedded in the ice core record. So we get CO2, we get particulate, and we also get the type of oxygen found in the air bubbles trapped in that ice core. Now you might say, the kind of oxygen, what are you talking about? Well, there are, just like other elements, oxygen comes in a couple different forms, and we call these isotopes, and it just has to do with the atomic weight of that element, of an atom of oxygen. During warm periods, the heavier oxygen 18 isotope is more abundant in the atmosphere. If you think about, if the Earth is warmer, it can evaporate heavier atoms of stuff. And when it's cooler, the atmosphere contains a greater abundance of the lighter oxygen type, or the O16 isotope. So scientists look at these ratios, the abundance between the heavier and the lighter oxygen. We call these delta or change in O18, O16 ratios, as a proxy, kind of a substitute, if you will, for what the global temperature was. This is really a brilliant way to constrain what Earth's temperature has been doing in the past by just looking at the relative abundance of these two oxygen isotopes. Slide 10. So from the ice core record, if we look at data since 1880 on CO2 levels or concentrations, we have a smooth line extending from 1880 to about 1960, which are estimated values of CO2, and that comes again from the ice core record. And then since 1960, approximately, we've been actually measuring CO2 levels up on the highest volcanic peak on the Big Island of Hawaii, and looking at CO2 levels. That's a good place to test or to measure CO2, because you're far from major land masses where industrial and automotive emissions are going to sort of tweak the CO2 levels. So we're getting a better glimpse here, if you will, of overall global atmospheric CO2 levels than we would if we took the data, say, from Hackensack, New Jersey. We'd get, extremely elevated levels there. So by taking the data from this region out in the middle of the Pacific Ocean, we're pretty confident that this is more representative of the Earth as a whole. So we can look at this graph and we can say, wow, since 1880, CO2 levels have been going up. And yes, indeed, they have, worldwide. We can also ask, why the zigzag line since 1960? Okay, notice once we actually start measuring the CO2 level, we see that although every year, overall, the CO2 levels are increasing, but we're seeing a slight dip and a slight rise and a slight dip and a slight rise every year in CO2. What explains that? Any ideas? So, yeah, you're right. It's the forests in the northern hemisphere. That's what's driving this, slight annual increase and decrease. So think about springtime, summer in the northern hemisphere forests, the greatest, most extensive forests on Earth. All that plant growth is taking in CO2. So that means that atmospheric CO2 levels decrease as the northern hemisphere forests are in their growth phase. annual growth phase. Towards the end of summer, fall, into winter, the trees drop their leaves, and CO2 levels increase because not only are the trees not taking in CO2, but the decaying of leaves and the decaying of any wood matter actually gives off CO2. So we can see here, just in this zigzag line, that the impact that the forests have on the Earth's atmosphere with respect to CO2 concentrations. So why do we care that CO2 levels are rising? Why do we care that the forests are having an impact on annual cycles in CO2? Well, we know from previous lectures, from our readings, that carbon dioxide, that molecule, that gas, is one of the really good gases at trapping or retaining heat in the atmosphere. And so as there is more CO2 in the atmosphere, the ability for heat to hang out for longer periods of time in our atmosphere is increased as a result of having more CO2 there. Slide 11. Another very important greenhouse gas is the molecule methane, or CH4. Methane has sources from certainly it's a naturally occurring molecule. It's basically what natural gas is made of. It also is produced as a result of garbage decay, or sewage. Treatment plants will give off methane in the processes that treat sewage. In rice fields or rice production is another way that methane is produced. And also the flatulence of cows and livestock produce methane. So human activities such as garbage and sewage and rice production and animal production, all of these activities potentially increase the amount of methane in the atmosphere. And so a couple of data sets here again from NASA are the top graph, or the top figure, shows surface methane concentration. So we can sort of see that there are hot spots, some hot spots. There's a hot spot down in South America. There's quite a few hot spots in Europe. There's a hot spot in Africa, on the eastern portion of North America as another hot spot. Places in the world that are producing more methane, Then if we look at the stratospheric concentration of methane, so going up above the surface of the Earth, it becomes more uniform. So in other words, the methane may be being produced in very isolated locations on the Earth's surface, but that methane is a very light molecule. It gets up into the stratosphere and then it just sort of spreads out around the world. And we have the ability for this molecule to trap a lot of heat. The other thing about methane is that even though there's less methane in the atmosphere than there is CO2, methane traps more heat per molecule than does CO2. Slide 12. So as CO2 levels increase, as methane concentrations increase, we have 4 graphs here actually. So we're seeing increases in global mean temperature over land. That's the graph on the upper right, And this covers approximately the same data set from 1880 through, say, the year 2010. So we have CO2 levels going up. We have global mean temperatures increasing. If we look at the 2 bottom graphs, the left graph looks at Arctic sea ice coverage. So how many millions of square kilometers for the last 100 and 110 years have been covered in sea ice? And we're seeing decreases in that, significant decreases in the amount of Arctic sea ice. And then the final graph in the lower right has to do with sea level. What has sea level been doing for the last 100 years or so and projected out into the next 100 years? And that's on the rise. So there is definite agreement in the scientific community that, in fact, human activities are impacting temperatures, which in turn are impacting sea ice coverage, which in turn are impacting sea levels, global sea levels. So we know that our activities as humans, the choices that we've made in our societies, are affecting global climate. Slide 13. Okay, but what about this 800,000 year record that we've looked at before? This is changes in climate, warming and cooling periods, rises and falls in sea level over the last 800,000 years. This was way before we started burning fossil fuels. This was before we started doing intensive agriculture, before we started, raising cattle. So there have been long-term changes in climate over geologic time that had nothing to do with us. So what are the causes, or what were the causes of these cycles in warming and cooling in Earth history over this 800,000 year period, and even going further back? But the 800,000 I keep referring to because this is our best data set. That's that ice core data that we have from Antarctica. We're really, really confident in that data set. So what caused this? Could it have been volcanic eruptions? A lot of people have proposed, volcanic activity, lots of ash in the atmosphere blocks sunlight, and therefore that could trigger a cooling period on Earth. Yes, but would it be this cyclical? Would it have this kind of pattern? Look at that graph right there. It's so rhythmic. It's almost like what's that graph you get if you get a heart monitor on, a cardiograph? It's too rhythmic to be explained by volcanic eruptions, because volcanoes don't erupt with that kind of predictability, or that sort of beat, if you will. What about changes in the output of the sun, what we call fluctuations in solar output? Yeah, the sun doesn't always emit the same amount of electromagnetic radiation. It cycles. We have solar flares. We have just changes in the amount of solar output. But again, does it do it on this very, very rhythmic kind of beat? And the answer is no. Slide 14. So one of the most brilliant minds of the 20th century, a guy by the name of Milutin Milankovitch, looked at some of this data, looked at these cyclical patterns in Earth's climate history, and he was a mathematician, he was an astronomer, amongst many other talents, and he came up with what are known now as Milankovitch cycles, looking at the Earth's relationship to the sun and how there is variation in our relationship, in our orientation, in our distance, in the way that we orbit the sun, that occur on geologic timescales. And this is something that he was able to derive using math and physics and astronomy. And what he came up with, which is the three components of this cycle, is that number one, the shape of the Earth's orbit around the sun is not always the same over geologic time. Sometimes we're a little bit more of a circular orbit. Sometimes we're more of an elliptical orbit, which is what we have currently. And we veer off of that orbit. We don't always follow the exact same path around the sun. Now, this changes over periods of something like 100,000 year cycles. The second component is our axial tilt. You guys know very well at this point that the tilt of our Earth's axis is 23.5 degrees. Has it always been 23.5 degrees? Will it always be 23.5 degrees? No, it is not. So think of a top. Have you ever spun a top? Okay, so spin a top in your mind, or if you have one handy, spin it in front of you. And you'll notice that the tilt it doesn't always maintain the exact same tilt. Okay, sometimes it might get a little steeper, sometimes it might get a little less steep, so that there's variation in the tilt of the Earth's axis, and this is going to affect our seasons. Now, the cycle at which this changes is something like 40,000 years. Every 40 or 41,000 years, the axial tilt kind of comes back around to where it was 41,000 years ago. And the third thing that Milankovitch identified is what's called the precession of the Earth's axis, meaning that wobble. So we talked about the fact that we're tilted, but then like the spinning top, we're also wobbling. So that right now we are pointing, the North Pole points at Polaris, right? What we call the North Star. But in every 26,000 years, the Earth kind of wobbles back or tilts back or points back towards the North Star. But every 13,000 years, it's going to point towards a different star. And in fact, in 13,000 years, it will be pointing at a different star. We already know mathematically we can determine which star. That star we have named Vega. So that in 13,000 years from now, the North Pole will not be pointing at the North Star. It will be pointing at a completely different star. But another 13,000 years after that, it'll point at the North Star again. So Milankovitch looked at these three components of our relationship to the sun and said, when all of these things line up at certain periods of time, you've got the 100,000 year cycle, you've got the 41,000 year cycle, you've got the 26,000 year cycle with these three components. Occasionally, they all add up together to diminish the amount of incoming sunlight. In other words, the Earth is a little bit farther from the sun, facing a little bit further away from the sun at either an increase in the tilt or a decrease in the tilt, and that all of those three factors combine to give us less solar radiation. That can trigger us into a cooling period or an ice age. Again, all of these components can combine to cause more incoming solar radiation. So he came about this from a very mathematical, astronomical kind of viewpoint and did the math, and then looked at the data set and said, aha, these things line up perfectly. So going back to that graph in slide 13, why do we have these long-term increases in Earth's temperature and decreases in Earth temperature and increases in sea level rise and decreases in sea level rise way before humans were doing the kinds of activities that we're doing today? It's because of our relationship to the sun. So this is what we call the pacemaker, if you will, of the ice ages. Okay, that's a term. I didn't come up with that term. That's a term that's been used. And it helps us to understand this larger, longer term global climate change pattern.